There's usually a transcription too, and if that distracts you, you can just like close it out.
No, that's fine.
Hi, everybody. Good afternoon. Thanks for joining us. We're going to get started in about 2 minutes. I just want to give people a little bit of a chance to start piling in. Okay, thanks everybody for your patience. I think we can get kicked off and I'll just keep admitting new participants as we go. Today's session, we're talking about high value measurement and verification options for commercial and industrial processes. I want to let everybody know we're recording the session. I might mute the participants just to eliminate background noise, but we do encourage you to ask questions. You can use the chat or you can raise your hand, and we will have a little bit of time reserved at the end for Q&A. With that, I'd like to introduce Eric Matzi, who's our IPMVP expert for today.
Hello, everybody. Good to see you. And welcome to, this will be actually the third, so I'll explain in a minute, webinar in a series on measurement and verification. So again, yeah, I'm Eric Mazzi. Good to work with everybody today. Just to confirm, now I'm forgetting, we booked this for 1.5 hours, up to 1.5 hours? That's what I thought.
Yeah. 90 minutes.
Okay. Thank you. Yeah, so there's maybe a couple familiar names there, but most people I don't necessarily recognize. So by way of introduction, my background is mechanical engineering and policy. I've been working in demand side energy management since 2007. Before that time, I did a lot of, you could say, supply side energy engineering and related to more electricity generation, consulting work, maintenance of district energy systems, a little bit of a generalist background there. I do quite a bit of M&V work with electric utilities, with one municipality, also with natural gas utility, and I'll share some case studies today on some actual projects. I do like to point out I do like and recognize the value of being certified. I have 2 certifications myself. One is the CMVP. That one is owned by Association of Energy Engineers, and then the Efficiency Valuation Organization, or EVO. They own the PMVA, and they also have another one called the PMVE for expert. And yeah, I do strongly recommend one of those 2 certifications for those who do work a lot in the M&V world, if you will. I am a member of the International Protocol Committee, the IPMVP committee, for several years, and I've also for several years been a trainer for the CMVP. I think last time, it's been mentioned a couple times, I think IESO probably still offers some sort of financial support for certain customers to get certifications. You could always check out your IESO contact for that. Okay, so what we're going to talk about today are so-called high-value M&V projects. So I'll define what we mean by that. And we'll look at it through a mix of some HVAC and industrial applications, and really through case studies. There's a little bit of background noise. Maybe we
I'm gonna
can
get that.
mute people, or I could maybe do it. Yeah, okay. Thanks, Megan. Okay. So we'll talk about what high value is, and we're going to do case studies. So the agenda is we'll do a little bit by way of review about operational verification, key parameter measurements, just a couple of basic concepts for M&V, and then we'll get into, we have 3 case studies, and then there's actually an appendix with a 4th case study if we have time. So the 3 case studies, one is for variable frequency drive or variable speed retrofit on a large institutional building for electricity savings. Another one is an industrial application for lumber drying kilns and converting the controller and these what are called circulation fans to variable speed controls. Another one is really valuable from an M&V perspective. It has to do with it teaches the lesson about the value of real power measurement versus just measuring amps or current for electric power, and then assuming the power factor or estimating the power factor. So we'll look at that. And then if we have time in the appendix, we have the M&V. We can talk about M&V for what's called a deep energy retrofit, which is a 14-story multifamily building for natural gas and electricity savings. If we have time, I'll get into that case study as well. So this abbreviations I use, there's listed here for reference, just to have those defined for you. And then, yeah, okay. So as I mentioned, this is the 3rd M&V webinar in this series, and we're really just starting from the ground up. So there was one webinar done in the fall last year that was Introduction to M&V. And then earlier this year in February, we did another one called Low Cost M&V Options. And both of these, as well as other webinars that are not just about M&V, are available at the Save on Energy site that's listed there. Okay, so a little bit about operational, the V in M&V. And by the way, I do encourage folks to raise your hand or just unmute yourself and ask a question if something comes up. If you have a question, I will try to monitor the chat at the same time I'm talking. If for some reason I don't see your hand raised or something, Megan may interrupt me or just unmute yourself. But we do want to have a lot of, I do like to have discussion, question and answer. Yeah, actually, before we get started there, let's do a little poll. Okay. So we're going to use this menti.com tool. And I'd like to do, so I'll put it in the chat. You go to menti.com and use the code you see 19665515. So if you go to menti.com and punch in that code, you can use your phone or you can use a computer and just describe how you see your role, like what is your interest in M&V? We got 4 responses. Let's see if we can get a lot more, maybe 6 times that. Right. 15 responses. Can we crack 20? Okay, well, maybe that's about it, but please do answer the poll if you can. Yeah, so all right, so we definitely have a handful of people who are leading, or would be the lead M&V professional. So you're going to have some experience, obviously, perhaps to share with the group, or you're part of a team doing it. I welcome your contributions and your stories, your anecdotes. If you're in the position of hiring someone, or you're someone who helps finance M&V projects, you may not be had the opportunity to be as familiar with some of the technical aspects, and that's fine. Okay, that's helpful. Tell you what I'll do is just to share with everybody. I'll go ahead and usually this works. I can put that in the chat. People can refer to that if you're interested. And let's get back to the PowerPoint. All right. And I'm going to get my pointer. All right. So this is really kind of review from the first two webinars in general. But operational verification is really where you confirm that measures are installed and operating. The main reference for M&V, not the only protocol, but the main one is, of course, the IPMVP, which is a reminder you can all get for free at evoworld.org, evo-world.org. That's shown later in this presentation. If you just open up a free account with a username and password, you can download the latest protocol as well as other resources. So there are also, as part of this webinar series, there's an operational verification template, a spreadsheet, and there's some other spreadsheets, and those are available at the Save on Energy site somewhere. I don't know if I have that link at my fingertips, but I'm sure we can find that for anyone who's interested. Little bit about key parameters and what they are. So key parameters, as it's defined in the IPMVP, over in the right here, it's critical variables, like over here, that have an impact on the savings. So another similar phrase I like to think is a key driver of the process. So when it comes to measurement and verification of, let's say, energy savings, of course, the energy, the electric power, or the fuel consumption, whatever the energy that you want or is to be saved, if you will, is of interest. But there's all these other key variables or key drivers of that process. And a key driver, the best definition I keep in my head is if that variable changes, then your energy consumption changes. So if it's an HVAC system in a building, outdoor air temperature, anytime any significant change in that outdoor air temperature, it will change the consumption of the heating, cooling, maybe ventilation systems. In a lot of industrial processes, sometimes outdoor air temperature is not a key driver. Electric consumption or fuel consumption in an industrial process might be very insensitive or independent of outdoor air temperature. So that's just one simple example of a key parameter is outdoor air temperature. Sometimes it is a key driver of the process, sometimes not necessarily. Another reminder is that M&V, this is Efficiency Valuation Organization. It's kind of link is shown down here. It sounds almost blindingly obvious, but you have to measure something directly on the system or the energy efficiency measure, or you cannot call it M&V. And that seems to be widely recognized if you're using ASHRAE protocol or ISO M&V protocols, as well as the IPMVP. If you're going to use data on another system or manufacture data, or you're going to use what are called deemed savings, those are all legitimate approaches, if you will. It's just that you're really not doing M&V if you're not measuring something on the actual system that's installed. Just as another review and reminder, especially in today's world of demand-side energy management, is energy efficiency is the most common type of project that M&V is used for. But increasingly today, and as we move into the future, it's definitely not the only kind of project. We are often getting into distributed generation projects like solar PV or combined heat and power, potentially with energy storage such as thermal storage or electric batteries, capacity management strategies such as demand response are used, or it's fuel switching, like switching to biofuels or electrification, going from fossil fuels to electricity. These are all strategies that are combined with each other, combined with energy efficiency. And the key idea is that there are these M&V methods apply to all these types of projects. You can go to the IPMVP resources, and there will be guidelines for distributed generation. There will be guidelines for doing M&V on demand response, for example. And M&V is commonly done on fuel switching projects. So by default, including this presentation and the previous webinars, the default is we talk about energy efficiency, but we also know that in today's world, in today's the world of demand side energy management, all of these strategies are needed to decarbonize energy systems, which is an overall driving goal for them in general. And again, M&V, by way of review, is a balance of the cost of doing M&V versus, let's call it, the value of the M&V. And so it really gets into what key parameters do we measure? Why should we do those measurements? What's the value of it? That's really some of the key messages here. And by way of wrapping up the review, I just want to say that no matter what your, for all M&V projects, whether they're quick and dirty, low-cost M&V or some of the more longer-term, high-value M&V, as we'll show the case studies we're going to talk about shortly, there's certain steps that you really need to go to for all M&V projects. And they're roughly in sequence here. So let's just talk about these for a minute by way of review. You want to identify who are the key M&V stakeholders. That will always be a project owner. That would be any organization that's kicking in money to finance a project. There are others. You want to understand or just think about what's the purpose and objectives for investing in M&V. Maybe that's driven by the financing organization, like a utility or a government agency or a green loan program. You want to describe the system and the measurement boundary. You want to identify, think about what are those key variables that might be needed to do something we call adjustments. In my opinion, you should always identify a lead. Who's that go-to person for the M&V? That person, that role should always exist, in my opinion, and not just my opinion, actually. I mean, that role can change over time. If it's a long project, the person wearing that hat might hand it over to someone else, but it's really important to have just who is the lead M&V professional. Ideally, in my opinion, that person would benefit from having a certification as well as experience. What variables are going to be metered and what equipment's going to be done. Definitely conduct a site verification. Document what the analysis and just, how the analysis will be done, and the who, the what, and the when of reporting. And I'm actually not surprised, but some of you may be surprised. I still get approached on projects where a lot of these things are skipped. So somebody just says, we're doing electrification project. What's the best M&V method? And all I can do, and what I do in a case like that is I pause, like, okay, what's the purpose of doing M&V in the first place? Who are the key stakeholders involved? Can you describe and lay out the system for me, or for yourself, just giving advice? Think about what are the key variables. Are you going to have a lead person? I had another professional approach me just the last few weeks. It's like, how do we do baseline adjustments with virtually no other introduction? So I had to ask, okay, what is this project? I mean, baseline adjustments for what? It turned out it was a mining operation, and they were doing ventilation upgrades and some other upgrades. We talked about what the purpose was. Well, they also wanted to not only verify savings, they wanted to build a model for forecasting future energy consumption for specific systems, such as the ventilation. But the very first question to me was, well, how do I do baseline adjustments? And I was like, well, we can't even start there until we get, the big picture. And my last comment is all these things do not take much time. You can get through this 9 boxes in an hour or less, probably, for almost any project. So they're just, to me, an important reminder. Just sort of lay out the items here, and that will help guide you to really a well-balanced, let's call it cost-effective M&V plan. And you really, the best practice is to definitely document these things in an M&V plan, which can be done rather concisely, by the way.
Thanks, Eric. We actually have a question that's quite related to some of the things you've been talking about. And
Yeah.
it's what's the granularity required for M&V? Can we use monthly energy data from invoices and Environment Canada, or do we need 15-minute interval data?
Yeah, great question. What's the interval data? I would say, that's another kind of question where it really depends on what's the purpose of the M&V. What is the type of project involved? Because it varies a lot. I mean, the range as a practical matter, the most granular data that's typically granular enough for almost any application that has a lot of variation would be 15-minute data. In other types of projects, doing what's called an option C, using utility meter with monthly data, is sufficient. Now, there's the pros and cons of choosing anywhere from 15-minute to monthly data has a lot to do with, well, how accurate do you need the results? How much does the process vary? If you're going to use monthly utility data and you have a lot of energy efficiency measures, you would not capture the savings associated with any of the individual measures. You would only get the net or aggregate effect. So that question comes back to, let's say, the stakeholders. Is that good enough? Do you need to know what the energy savings of individual measures are, or is it good enough just to know the net aggregate effect? That would lead to answer the question like, do I need to submeter individual systems with, let's say, 15-minute data or hourly data, or can I just use monthly utility bills? And then the cost, the M&V cost between those, let's say, two range of extremes, from, let's say, submetered 15-minute data to utility meter monthly averages, the cost is very different. So good question. I hope that answers. Any other questions at this point? Because we're kind of moving into the case studies next. But that's a great question. Okay. Now, pardon me, I caught a cold last week. Not the best timing, but to keep my throat hydrated here. Okay, so when we talk about high value M&V, this little chart helps illustrate. So one of the ways to think of it is, how much does your baseline energy, or maybe you can just throw your post-install or what's called reporting period energy in there as well. How much does the process energy vary over time? And then on the x-axis or horizontal, I mean, how much does the project cost, or what is the monetary value in relative terms? If it's high cost, high value, or is it low cost, relatively low value, but obviously still worthwhile? And is there a lot of variation? And the more that it's higher variation and higher cost, higher energy saving project, we're in this upper right quadrant where there's a lot of variation and more higher value of the energy savings, let's say, as monetized through the utility bills. So that's what we mean by high value M&V. So it's really M&V projects that tend to cost more money, meaning the M&V activity itself is a larger investment in metering and people's time, but it's worth it, as we'll hopefully see with these case studies. And as a reminder, back to the first two webinars, I mean, our last webinar was all about low-cost M&V approaches. So you can go back and look at that if you're leaning a little more towards the other of these three quadrants, if you will. That low-cost M&V webinar would apply a little more outside of this upper right quadrant. But this is what we mean by high value. Adjustments, last reminder, it's always, M&V is about quantifying the energy savings from your baseline versus your post-install or reporting period. And when the energy consumption of those two conditions needs really to be normalized to the same operating conditions, such as outdoor air temperature or production rate or occupancy of a building, an endless list of examples of different variables that might change between your baseline and your post. The way I like to describe it, real world projects are like uncontrolled experiments. So all of us, pretty much all of us, I'm sure, had, let's say, high school physics or something, or college physics, where we did benchtop experiments where you can control all the variables, right? Except for the one that you wanted to quantify, like how much energy does it take to do this or a force to move that. So laboratory experiments, you can control all the variables and you don't really need to necessarily make adjustments for what would be called confounding factors that are beyond your control. But in real world projects, we don't have that ability. You cannot operate a building and dictate what the outdoor air temperature is. It's going to change. And if that will affect your HVAC energy. So adjustments need to be made in order to account for those changes in variables that do affect energy consumption. And again, this will be review for many of you, which is they tend to fall into two categories: is variables that we expect to change, we'll call them routine adjustments. Variables that we don't expect to change but are still significant will be called non-routine. And it is, note that some variables like hours of operation could fit into one category or another. So if we don't expect operating hours to change and then they do change, we call that a non-routine adjustment. For some projects, we do expect operating hours to change, so we'll just call that a routine adjustment. So, all right, first case study, variable frequency drive on a large institutional building ventilation. So we'll just run through what the project involved. So the stakeholders were, of course, the facility owner. And by the way, that will always be a stakeholder. Every building, every plant, every physical system, somebody owns it. Some person, some organization. The users of the facility are stakeholders. In this case, there was a utility providing incentives. So this was a large institutional building for research and teaching, over 500,000 square feet. The project involved retrofitting fixed speed ventilation systems. So there are a bunch, like 26 fans ranging from 25 to 50 horsepower each. They just ran 24/7, 365 days a year at full speed to ventilate. And the retrofit was to put all those fans on variable frequency drive for variable speed control. Before the project, the savings were estimated at about 1845 megawatt hours per year in electricity savings. By the way, in these case studies, they are all real case studies. However, the numbers, there's a lot of changes to the numbers just to keep the retain the anonymity of the actual project. But they're not changed so much as to change the meaning of anything. So in this one, let's say the pre-project estimates were, 1845 megawatt hour per year. That's 1,800,000 some thousand kilowatt hour per year. The chosen M&V method was a retrofit isolation called option B in IPMVP terms. Metering was set up with DENT 3-phase power meters. 15-minute intervals was worthwhile. As it turned out, we had a 12-month baseline period, and for certain reasons, the reporting period ended up ranging for some of the fans anywhere from 552 to 754 days. So that's, yeah, over 2 years for some of the fans for reasons that I'll mention. As a general reminder, or for those who weren't aware, when you have VFDs are part of the system, and the VFDs consume power themselves. So that needs to be counted and measured in the M&V. I'm sure many of you know this, and just as an example, on the left here, we have a chart that shows the VFD efficiency, which means the VFD efficiency of 98% would mean that the VFD itself consumes 2% of the power that is fed to the motor. And that VFD power consumption, or VFD efficiency, if you want to call it, it will change with certain variables such as motor torque or load. It will change with if there's changes in the system voltage, and of course the speed. Just as by way of another example on the right, we have an industrial VFD spec, about 2970 horsepower rating. So the VFD efficiency, this is just straight from the manufacturer, ranges from, depending on load and speed, but it ranges from about 3% to 10% of the power input to the VFD motor system. Roughly 3% to 10% of that power would be consumed by the VFD itself. And that needs to be accounted for in the measurement. That's a new load in the system compared to the baseline. These are the 3-phase power meters that are commonly used in M&V. Roughly less than a year ago, these were the rough costs it would take to put in these. So we had, I guess it would have been about 25 to 30 of these meters installed for this project, for the 12-month baseline and the, I guess, over 2-year reporting period. These are some of a sample of a summary of the results. Okay, so we had no data or no reason to do any baseline adjustments. By the way, if you're still not fully clear what baseline adjustments are, we can answer during Q&A or review the first 2 webinars. We had interim M&V done where the savings came out to about 1.7 megawatt hour per year savings. That's compared to 1.8 was what was expected. It was discovered that one bank of fans was still operating at 100% of full speed. And so in this chart, this just shows for one fan or one bank of fans. So I don't think this was not the one that had not been programmed correctly, but the blue was the pre-retrofit or baseline. There was a commissioning period here, and then the post-retrofit is in green. So you can see the power consumption came down, right, quite a bit, from roughly 35 kilowatt to, I don't know, roughly 17, 18 kilowatts, something like that. So an important event from this case study is that based on the interim M&V, there was an investigation done into, well, why are the savings not coming out as expected based on the estimate partway through the reporting period? And it was found that, yeah, it was maybe 2, I can't remember, but there were several fans, maybe 8 or 10 fans that were just not, they had the VFD installed, but they just didn't get programmed to modulate. They were running at 100% speed, which meant they were consuming actually more power than the baseline because, again, backing up, VFDs consume power themselves. So if you take a system that's running at constant speed, motors, and you add VFD to the system and just run it at 100% speed, you're going to consume more than your baseline because you're not only consuming the baseline motor power, you're adding the load of the VFD itself, the consumption of the VFD. So that is what was happening in this project. And then after some what's called forensic investigation and some reprogramming, and we allowed all of the fans to run through at least 12 months of post retrofit, then the final savings came out to over 3,000 megawatt hour per year. So it was about 63% higher than the pre-project estimate, and it represented roughly 60% reduction from baseline. So some of the key lessons from this is that the best value M&V is not always the lowest cost. This project, even though it's a large building, it was a very simple project in many ways, and arguably the stakeholders could have said, well, there's no need to do M&V here. What could go wrong? Right? You put VFDs in, what could be simpler than that? You program them, they modulate. You should see your power savings. Why do M&V? Well, M&V was done because of the stakeholder requirements, namely the utility funding contribution, and it was found that one of the key lessons, the value of doing what's called interim M&V. So if you have a project and you're going to run whatever X number of months of the reporting period, the best practice is to do not wait until the absolute end of the reporting period and then tabulate your results. Because if you see things are not performing as expected, then you've potentially missed the opportunity to make some corrective action, kind of wasted some time. And so this, through the corrective action, right, the savings went from roughly 1,700 megawatt hours per year up to 3,000 through, and that would have not happened without doing M&V. I mean, who knows? Maybe someone would have eventually discovered it. Who knows how many years later? It's just backing up. Another basic lesson is it's important to measure real power. Make sure you capture the VFD or any important load in a system. This M&V took a long time, and not a lot of people have, let's say, the patience for that or would appreciate the value of doing that. It doesn't mean that there's a lot of activity and chewing up a lot of hours over the 700 and some days of the reporting period. It just means somebody maybe is downloading data every month or two and checking the numbers. It's not like you have full-time people on the job. But this one took a 12-month baseline period. For whatever reason, it took roughly a year to get things installed and commissioned. Took another 24 months of the reporting period plus analysis. So this was like a 4-year M&V project. That's actually quite a long time. So I'll pause for any questions or comments on this.
We did have a question related to time, actually. It might be better to do as a dialogue. This person seems to have an anonymous name or just the letter A, but if you wanted to come off of the mute and ask your question. Sounds like there's a specific project in mind. Otherwise, I can just read it. Yeah. If I install a power meter or data logger plus an amperage sensor for capturing 2-minute interval data, would there be a set amount of time I need to keep it installed on a motor?
Yeah. Okay. First, I guess these questions, I'm not seeing them in the chat. Maybe it has to do with my settings, but that's a detailed question. Okay. Setting up, I heard in the question you're metering power or amps. Those are related or both. Okay, fine. And when we get to the third case study, there's an important distinction to those in electrical systems, the difference between amps and real power, which we'll get to in the third case study. But that really comes back to the question is, we're doing 2-minute intervals, and how long should we do that? Well, there's no one answer to that. It really comes back to, I would say, let's get the judgment of the designated lead M&V professional, because what that person would take into account is how much does the process vary. So again, you want to run a reporting period long enough to capture all of the significant process variations. I mean, that's the general technical guidance that I would provide, or that you will get from M&V protocols. I mean, it's just, I would say, basic science, common sense from that perspective. If you're doing a cooling system and if it's a cooling system that only operates, let's say, during the summer season, and your reporting period happens to conveniently start during the summer, you might get by with a 6-month reporting period. If it's a cooling system upgrade and it's commissioned by October 1st in a given year, you're going to have to wait 6 months for the next summer season to start, right? Where you can capture it. So you're probably just going to have to run for 12 months anyway. Some industrial processes do not vary with outdoor air temperature. You could have, well, in fact, the next case study we're going to talk about, we settled on a 6-month reporting period. Okay, so related to that question is, how long should you collect data? It has everything to do with capturing all the process variations and how accurate do you want your M&V results to be. Now, it wasn't part of the question, but I would question, why do you need 2-minute intervals? 2-minute intervals is a lot of, I mean, with 15-minute data, you get about 35,000 readings per year. So you'll get like 7 times that, 7.5 times that if you're doing 2-minute data. So then you're going to get, I don't know, like 250,000 readings per year, 2-minute data. I had one project, it almost seems like, if you're upset with somebody, or, I'm just saying in humor here, but if you don't like somebody, just give them what I must have done something wrong once. I got 30-second time average data. I mean, if you get 30-second data, you just end up with these huge unmanageable spreadsheets, right? So, more time intervals, it gets unwieldy in terms of, sharing files, or just unnecessary detail. And if the process doesn't vary much, why have 30-second averages? Why have 2-minute intervals? At the same time, it has to do with how much does the process vary, and maybe I need to do 2-minute intervals to capture. So that's my best answer to that question. There is no one size fits all. It has everything to do with how much does the process vary and how accurate do I want my results to be. That drives the interval of taking your averages, and it also guides the decisions as to how long do we, let's say, run the reporting period, or the baseline period for that matter.
Thanks, Eric. There's a couple more questions as well.
Yeah, let's go.
What were the critical variables identified for this case study you were just presenting?
Yeah, again, there were no baseline adjustments. So we did not have we did not do adjustments. The ventilation was driven by I'm just going by I'm pretty sure it was now I actually don't remember if it was I think it was CO2 monitors, sensors tied to the VFDs. It might have just been operating schedules, but now, to be honest, the details are a little fuzzy. But we did not have, it was decided that there was no need for adjustment. So we didn't have there was no need to adjust the energy for outdoor air temperature, because that actually was not a variable that directly affected the ventilation settings. It was about occupancy, and there was either very little change, or there was just no data available. And that's actually, yeah. So that's, I could carry on a little more, but that was the basics there.
Great, thank you. One of the other questions was, please elaborate why there was no adjustment required to the baseline. And I think you just answered that as well.
Yeah, and again, I'll say very often, especially for buildings, you would really like to be able to do adjustments for occupancy, but if you do not have the data to do that, then you cannot do the adjustment. So sometimes the adjustments is, yeah, we think it's important, but we have no data to put numbers to it. And there's another nuance there, which is if your energy data are 15-minute readings, I mean, technically, let's say mathematically, you would want 15-minute data readings on, let's say, occupancy. I mean, maybe CO2 is indoor CO2 levels. Like if we had indoor CO2 levels somehow averaged for this large building over 500,000 square feet, we could have potentially used that data to at least examine whether adjustments for CO2 levels baseline versus post would have been worthwhile. But that's the other practicality of real world projects is often in a retrofit like this, let's say maybe the CO2 sensors were put in as part of the VFD, but you had no baseline data for CO2 levels. And CO2 levels were your measure of occupancy. Well, you cannot do, you can't build a baseline model of baseline energy consumption versus CO2 level to carry out an adjustment if you have no baseline CO2 data. Does that help answer the question? I hope Forever had that. Yeah.
Yeah, really good. Thank you.
Okay. Okay, we'll move on to the next case study, a lumber drying kiln. This is an industrial. So this is not the actual, this is a stack of lumber. I got a picture off the internet. I'm not showing the real process here. So this is a project that did involve 5 lumber drying kilns. They dried certain type of product that's not actually the traditional dimension lumber you see here, but something else. So in short, there's a lot of, it's a conventional lumber drying kiln that it's shown in the upper right here, where it's a batch process. And what that means is the kiln is opened up and then a skid of lumber is put in there. There's a heating source in there burning natural gas to provide heat. There are circulation fans and it is vented to remove the moisture. So the heating of the lumber, moisture evaporates, and until there's a starting moisture content and then there's a final moisture content. And so the measure of quality in this kind of process is percent moisture. So once it gets down to the targeted moisture based on how it's measured, and they also look for percent defects, those were measured. Those are the key metrics involved. So in the baseline system, the project was, I'll just run through here. So the stakeholders was facility owner. There was a utility providing incentives for the electricity. So it was a lumber drying operation. It was natural gas fired heaters in this lumber drying kiln. The baseline was fixed speed. The energy efficiency measure was a new controller plus VFDs to drive the circulation fans. And it was VFD on the burner fan as well. The again, not necessarily real numbers here because I've altered things, but the savings were around 1 million kilowatt hours per year estimated pre-project. We went with retrofit isolation, IPMVP. We used 3-phase power meters. We ended up with a baseline period of 12 months of production, but we only had about 2 weeks of baseline power data. And then we ended up going with a 6-month reporting period. I'll just mention why only 2 weeks of baseline power data. Well, this is one of the real world logistical issues with M&V is once a project gets approved and some equipment needs to be installed during a shutdown, sometimes there's a really short time period. It says, okay, the project is approved in March. Our next shutdown is, let's say, June 1st. That really narrows your window for collecting baseline data. And there's a lot of judgment that has to go into it to say, well, is that enough time? Can we get enough data that's we feel is sufficient for this project? Who's the we? Well, it comes back to the stakeholders involved with the guidance of the lead M&V professional for a project. And the long and short is that was good enough. We did get 2 weeks of baseline power data. The process did not vary much based on outdoor air temperature, or at least not to a degree that we could not work with that. And for similar reasons, the facility owner wanted to keep the reporting period shortened. They wanted to get the results. We had enough data, so we did not feel the need to go 12 months. So there was a power supply driving all these fans. There was like a proprietary algorithm built into the whole process. So it was not just variable speed operation. It was actually metering things like temperatures, humidity levels, used to modulate firing rate of the burner and also the speed of the circulation fans. And we had the DENT 3-phase power meters you can kind of see here on the right. Excuse me. So one of the outcomes of this project, which from one perspective was really good news, from an M&V standpoint was introduced some tricky complexities, which is the measure of production in a lumber kiln is board feet. One board foot is just defined as a piece of wood 12-inch by 12-inch by 1-inch thick. That's a board foot, or FBM is the abbreviation that's used for that type of manufacturing process. So the baseline was, let's just say it was 13 million board feet. And in the reporting period, it scaled up to an annual rate of about 17 million board feet, about a 30% increase in the production. So again, it's a batch process. And due to the improvements in this control system, it was actually very good news for the owner that they could dry 30% more lumber every 12 months because of this retrofit. Now, that introduced some tricky issues in the M&V, though, because that's what's called a rebound effect, right? So rebound effect, I guess I can talk more during the Q&A, but the long and short is a rebound effect is where the energy efficiency measure leads to an increase in the activity. In this case, the activity is the production of dried lumber. So that technology itself is what enabled and triggered and caused an increase in production, which actually was a good thing, because in manufacturing, anytime you can squeeze more production out of your existing equipment, you're a hero, right? That has good economic value. But one of the tricky parts from M&V is that the baseline system was in no way capable of producing 17 million board feet of production. So that meant, okay, how do we approach baseline and reporting periods to be on the apples to apples operating conditions, especially the production rate as measured in board feet? I won't spend too much time on this because we would need more time, but you could say, well, we'll just truncate, we'll reduce our reporting period hours till they match the baseline, and we'll do it that way. We could assume we had increased baseline hours to achieve the production that we actually measured for the reporting period. Well, the problem with approach number one is that's not actually consistent for specific reasons with M&V protocols. The problem with approach number two is there's just not enough hours of the year. It would have taken about 11,000 hours per year. There's only 8760 hours per year, so that's just physically not reasonable. So what we did do is that we set the baseline hours equal to the reporting period hours. So what that meant, practically speaking, is you can go back and review the first two webinars, but essentially your M&V savings is your adjusted baseline energy minus your reporting period energy, and using the avoided energy approach, which we talked about in the first two webinars, one of them or both of them. So the reporting period energy was our measured average kilowatts of the fans in the post, times the operating hours of our reporting period. And then what we did for the baseline is we took our baseline kilowatt, our average powers, and we multiplied by the same hours as the post. And that came up with our annual energy savings. Kilowatt times hours is kilowatt hours. We get two numbers, we subtract them. This was consistent with what was in the M&V plan. Now, the facility management and another consultant involved with the project actually requested and proposed rather strongly that a different approach was used, and they wanted to use an energy intensity metric, which is kilowatt hour per board foot. And their proposal was to take the kilowatt hour per board foot for the baseline and multiply that by the board foot of the post, so the higher production rate. And that would produce a larger electricity savings number. The problem was it's physically impossible. Like the baseline system could not produce that number of board feet per year. It could not dry that quantity of board feet per year in the baseline system. The only way it was even theoretically possible is if the baseline fans would have operated, anywhere from 15% to 45% above their rated capacity for all operating hours of the year, which of course is impossible. The motors would have burned out. So the proposed, what would be called counterfactual, was just physically not possible. And the baseline system just did not have sufficient capacity. And also the energy intensity approach was not in the M&V plan. And so it was done with, so the results were done as I showed 2 slides back. So instead of just over 1 million, or let's say over 1,000 megawatt hours per year, we got about just over 900. It was still pretty good, about 84% of estimated. Very importantly, the drying time was reduced and the board feet production capacity was increased substantially, as in by 30%. This project happened to be received funding for the electricity savings, but there were no stakeholders other than the owner who had an interest in the natural gas savings, so those were not M&V'd. Like the facility owner literally said, I'm comfortable, we're getting gas savings, it's not part of the M&V. So there was absolute savings in electricity of 902 megawatt hours per year, and with a simultaneous 30% increase in board foot production. I mean, that's a very successful project. So the key lessons of this, well, it has some lessons around the rebound effects and the use of energy intensity in M&V. When you have rebound effects, there's just decisions to make, which I illustrated a few slides back with those 3 options. Just how could you adjust the baseline energy if the pre-retrofit or baseline system was not capable of delivering the post-retrofit production? Now, I do want to mention that some stakeholders, they do not care about rebound effects. And some do and some don't. I know I've talked with people like from U.S. Department of Energy at conferences in the U.S., and when the U.S. DOE gives incentives to industrial operations, they don't care about rebound effects. They actually do commonly just use the energy intensity metrics. They're happy with that. And it's just a different approach. So it isn't always the case, but when it comes to utilities, especially electric utilities, where the funding is predicated on seeing absolute reductions in electricity to justify providing money from the general ratepayer pool of funds, they do care about rebound effects. And then the other was, I mean, in this project, there was some disagreement about using this energy intensity approach versus the approach that ultimately was used. But it was what helped resolve that difference of opinion was there was a clearly documented M&V plan that was provided as part of the financing agreement upfront. So when that owner signed the agreement to receive funding for this project, that person had already seen and reviewed the M&V plan, which is an important part of the funding agreement. And so that just helped resolve those different, there's still differences of opinion, but ultimately it was agreed, okay, that's the M&V plan, we'll go with it. So any questions on this case study?
I don't have anything in the Q&A section for this case study, but if anybody does have questions, please go ahead and speak up.
Okay, well, we'll move on to our third and final. This is an industrial 500 horsepower motor shutdown. This was in a biomass handling system on an industrial plant. Again, in this project, just to run through, it was a facility owner, there was a utility incentive involved. Obviously, the facility users, maintenance and operations staff, they are always considered stakeholders, certainly in my opinion. There's a forest products operation. So this project had more than one energy efficiency measure involved, but the largest measure was to take a 500 horsepower motor that was idling, well, was operating 8,500 hours per year. And actually the plant staff identified this as an energy saving opportunity because they said, well, it operates 8,500 hours per year. It only needs to operate about 250 hours per year. The plant technical staff estimated that it consumed 159 kilowatts. And so estimated electricity savings were based on that number, which I'll show coming up. I think maybe it was, anyway, I'll show the number. It was again chosen to do an option B method. We used, again, DENT 3-phase power meters. So the baseline data, it was another situation where we had 12 months of production, but we only had motor amps or motor current spot readings for the baseline. So there was no 12 months of power measurements for the motor in the baseline for those 8,500 hours per year. It was just motor current, not real power, not kW, but motor amps that was measured, which I'll talk about. And then it ran a reporting period of 6 months because that was enough and it wasn't seen as particularly sensitive to the variables like outdoor temperature. Oops, I skipped a slide here. There we go. So this is a power meter for the whole system of measures. So this is 15-minute readings, and there was a short baseline period of about 2 months. And that was another logistics issue where the project was approved. We collected baseline power for as much time as we had until a shutdown, and then, or to the change of operation from idle, reducing the operating hours. But we decided it was sufficient. And then we had, pretty much a little longer, but we had a good solid 12-month baseline period, reporting period here. Now, one of the things you can see from this is that the estimated power savings from the one motor alone was 159 kilowatt. I can't show you all the details, but this chart here included the power of that one motor and some other measures involved. And one of the key issues here is that you can see up here, the baseline system, including that motor and some other measures, did not actually consume 160 kilowatts, did not consume 159 kilowatts. So that means it's impossible to save 159 kilowatts for the one motor if the entire system did not even consume 159 kilowatts. You can't go from, even if it went to 0, you could not save 159 kilowatts. So we knew the savings were not going to come out as estimated. So this table here summarizes the results. Okay, so let's talk about the pre-project estimate. So the pre-project estimate of power savings and energy savings was you could go from 8,500 to 250 kilowatts hours, 8,500 hours to 250 hours. So that's a change in hours of 8,250. It was 159 kW for those hours. And so the savings was 1312 in megawatt hours per year savings. So where these came from spot readings of motor amps, motor current, and assumed power factor of 0.8 on this induction motor. So that was the pre-project estimate, and the incentive was approved. An M&V plan was written and included in that incentive agreement. And then baseline measurements were done for about 2 months, and it turned out that that one motor consumed about 47 kilowatts of real power. The plant staff, technical staff had estimated based on spot readings that it consumed 159 kW. So the M&V was based on those dense three-phase power meters installed collecting 15-minute intervals. And actually, the M&V field team supervisor, who's a ticketed electrician with decades of M&V experience, actually took temporary instruments to the site and did some spot readings with a portable real power meter and verified what the DENT three-phase power meters were showing, and also measured that the power factor was actually more like 25% or 0.25, and the motor loading was estimated to be around 9% motor loading, which meant it was mostly idling. And so the actual change in hours turned out to be 200. It went from 85, 84 to 265. So the change in hour estimate was roughly pretty accurate. The baseline power was 47. The M&V was 32 kW. So the savings was about 15 kW. And so the actual savings came out to be about 395 megawatt hours per year, or about less than a third of what was estimated. And what this has to do is, excuse me, a lot of the motor, a high proportion of those motor amps measured in the baseline were magnetizing current. It was not for real power. If that doesn't make sense to you, I mean, you'd have to just do a little review and background on electrical engineering and electric power systems, and that you have magnetizing current, magnetizing power, you have real power, and the energy savings is based on real power savings. And so you could say there was some time and resources were attempted to be saved in the pre-project by just using motor current readings, spot readings to estimate the baseline power. But as it turned out, it was overestimated by more than a factor of 3, what the real power consumption was. And so therefore the savings came out at about 30% of what was estimated for the purposes of the incentive. And so the key lessons here is, it is best to measure real power. This project showed the potential consequences of doing that. Now, it is a common practice where motor current is monitored. So especially a lot of industrial plants, it's in a way, it's free data, meaning there's already an ammeter installed that's attached to, let's say, a dashboard and a data historian. So it looks like free data. And all we need to get real power for these induction loads, like an induction motor, is we need to come up with a realistic power factor. And in many cases, that can be done. However, in this particular case, that was not, it was way overestimated what the power factor was. The power factor was assumed to be 0.8, just based on experience, and the measured power factor was 0.25. So you can just see your real power, even if the amps are correct, 0.85 divided by 0.3, that just meant the real power was overestimated. Let's do the quick, what's 0.85 divided by 0.3? Sorry, divided by 0.25. Yeah, 3.4. So real power was overestimated by a factor of 3.4 using this formula and the incorrect power factor. So the lesson is, if you do rely on measured amps, you want to be very careful about what power factor do I use to calculate my real power. And I'll pause for questions on this third case study. Any questions? You can raise your hand, or I guess, is there a separate Q&A? There must be a separate Q&A channel that I cannot see. So
Yeah, I'm keeping an eye on that, but
sure.
oh, one just came into the chat.
Yeah, I see. What is suggested motor load factor to use? Good question. Now, motor load factor, I didn't actually talk about load factor. That's different than power factor. Motor load factor, we talk about this in the CEM. How many of you, by raising your hand, have taken this Certified Energy Manager or CEM course? See, we got Edwin, somebody from Ontario, Robert, Alan, a handful. Yeah. Motor load factor. I just taught the CEM a couple days last week. Yeah, so motor load factor is equal to actual motor output power, or let's call it kW, divided by rated or nameplate output kW. So that's what motor load factor is. So that in this case, the motor was that ratio was about 9%, which I did estimate based on some real power ratio. I could take more time to explain that, but the actual motor load factor I estimated using the real power ratio, and I believe that's where I came up with the roughly 9%. It's a good question, Edwin, because okay, yeah, so power factor, of course, is equal to it's on the electric side, so it's your electric real power in kW divided by your electric total power in units of kVA. So it's a ratio of kW to kVA. It's the electricity. It's a parameter based on the electric power supply, whereas motor load factor is all on the mechanical side of the motor. Because, yeah, I can maybe show you even a diagram here, which I think I have handy, which may only just take a moment. I'm almost there. Yeah, like this diagram here. Right, so motor converts electric power to mechanical power. So motor load factor has to do with this actual motor output divided by the nameplate rated motor output. Power factor, I know this wasn't exactly your question, but is going to be your PE or real power divided by your PS, the symbol for total or apparent power. So power factor is all about the red color-coded electric power supply, and motor load factor is all about the output mechanical power. And so, yeah, maybe I'll just say one more thing, Edwin, motor loading, power factor, power factor does vary with motor load factor. So three ways to estimate motor loading are use amps. Well, I'll say measure amps, measure RPM, measure input real power. This is sort of getting a little bit digressing, but yeah. So, and let's see. I guess it's Sky asked a question, can use power factors on an electricity bill? Generally, no. You would want the power factor for the specific piece of equipment that that you want to measure the power. If it so happens that, let's just say, this 500 horsepower motor was a very high proportion of the total load that's on the utility meter, then sure, you could do that, but that is not the case here. Yeah, you want to get the power factor for the specific motor or loads of interest that you're going to do measurements. Yeah, so again, the key thing here is motor amps are often readily available, and you really want to get real power, and then it's very easy to assume a power factor and estimate your real power. But in this case, somebody got bitten, if you will, because it was severely misestimated, the power factor, so that the real power was really misestimated. Yeah. Okay, so we still have, gosh, 13 minutes. Just by way of wrap up, we have, there are some free resources. If you go to efficiency evaluation, I guess the website links, I'll just type it here, or it's...
Well, I did add it to the chat earlier as well.
Oh, you did? Oh, okay, yeah, evoworld.org, or just Google bpa.gov. They actually have a lot of great, yeah, a lot of nice free resources. Sorry, not BPS, bpa.gov, Bonneville Power Authority, and just Google M&V reference guides. You'll find it very easily. ASHRAE, it's not free, but the 2023 ASHRAE M&V protocol is pretty good as well. All right, so we have questions. There's a link for further information, further inquiries. I do have another case study, but let's see. Looks like Andre, you have your hand raised. You want to go ahead? Or Andrew, excuse me, not Andre, my bad. Andrew, have your hand raised. You want to unmute yourself and go ahead? Okay. No problem. Richard?
Thank you. This is just a question on the case number 3. So I noticed that for the reporting for the baseline, we use 2 months. We only have 2 months data available, but for the reporting month is 6 months. So how do we so the operation hour will be different. So how do we adjust that?
Yeah, it's yeah, so what basically just projected, we use the power, we use the post, we projected 12 months of we projected, use the 80, so the savings would have been, I'm just going by, it would have been 85, 84 hours. So 85, 84 hours minus 265. So we
Okay.
had a savings of 83.19 hours. And then we had a savings of about 15 kilowatts. So 83.19 hours times 15 kilowatts. That doesn't add up. Okay, no, I know why, because I changed numbers, but we used essentially the reporting period hours and then the difference between baseline power and reporting period power.
Oh, okay, I see. So meaning the time period is selected not for operation hour, it is for basically for the power reduction purpose, right? I guess that's what it is.
Yes,
Okay,
exactly.
gotcha.
Yeah.
Thank you.
Yeah, and these numbers are yeah, these results are pretty similar to the actual results. The numbers are changed a bit. It also included other measures besides the one motor. So these numbers are not going to add up. And
Yeah,
that's
fine.
actually partly intentional because I want to share a real world project, but we need to retain the anonymity of the actual project.
Definitely.
So,
Yeah. Okay. Thank you.
but these
I got it.
numbers are the 159, that's a real number. 47 is a real number. 32 is a real number. These hours are real numbers. Yeah.
Okay.
So, but that's how we did it. Yeah. And that's pretty common. For those who've maybe done M&V analysis, if you use the reporting period hours and then you multiply, let's say, by the difference between baseline power and reporting period power, what that means is you're using operating hours as a routine adjustment in your calculation. If that doesn't make perfect sense, that's fine. That's how it works in the details. That's pretty common in industrial. Yeah.
Thank you.
Yeah, good question.
Richard, I think you had another question about the rebound effect.
Yeah, actually, yeah, you reminded. Thank you. Just for the second case, scenario is if the electricity usage after during reporting period is more than the electricity usage during the baseline period. So, but however, due to the rebound effect, how do we evaluate this? This project is it going to be a success or are we going to consider the failure?
Yeah.
How to do that?
Yeah, great question. I mean, okay, it's a great point, Richard. You said the electricity, just for everybody's benefit, the electricity consumption during the reporting period is greater than it was in the baseline. It could be rebound effect. I mean, the first question is why is it greater? Okay. And if it has to do with production increased in the reporting period relative to the baseline, then the next question is similar to this project is, well, one of the general question is, do the stakeholders involved care about rebound effects or not? Because I mentioned, I know this has come up at conferences with U.S. Department of Energy when they've given funded projects, they didn't actually care about rebound effect, which is fine. They didn't have to. They viewed it as a non-energy benefit that production would increase, which of course is very much true. And by the way, utilities recognize that as well. It's just that their perspective is, well, yes, it's wonderful that our customer realized a non-energy benefit of their production increase. It's just we cannot, we should not be contributing a lot of funds out of money that came from the general ratepayer base. So I don't know if that fully makes sense, but that's the logic there for utilities is that we should not be incentivizing individual customers funded by a broader set of customers to increase their production. We need to justify it on avoided electricity consumption by our rules. So yeah, the ways you can handle it, I mean, these are the options we came up with in this project. How do you handle rebound effects? I guess that's my best answer in short without getting into the details of
That's fine.
the other.
Yeah.
Yeah.
Okay, really appreciate it. Thank you.
Yeah. And then let's see, Edwin, you have a question in the chat. It says, I'm interested in calculations for space cooling equipment, package roof time. Yeah, well, the last case study, which I really don't have time to go over, has maybe some of that. I would say that probably you're going to, if you look through the Evo World website and the IPMVP resources, you will probably find some examples of space cooling equipment, M&V, in some of those application guides. If you do the probably either one of the certification programs, the CMVP or the PMVA, you're probably going to get some cooling applications. But yeah, I have examples. I guess nothing I'm going to be able to whip out in less than 4 minutes, which is what we have. I don't know. I think these slides, Megan, are these slides made available to people?
Yes.
So it might be somewhat, the extra case study is in there, but it's not actually cooling, it's heating with gas absorption heat pumps. There might be a little bit of information there, but that's not really exactly what you're asking. Yeah, I will say, like, the people have follow-up questions. I mean, I can be reached. I guess I'm at the title slide. I had my email address, mcs@telets.net. So yeah, if Edwin, you want to email me and you had a specific, I might be able to direct you to something. Just send me, and that's open for anybody. There's my contact.
Thanks, Eric. You can also always email training and support at ieso.ca. And that is our team and all of our partners, such as Eric. We usually try to set people up with the best partner to respond to their questions. But we offer what we call post-training support. If you attend any of these sessions, you can always reach out to us at that email and we'll get you in touch with the support that you need.
Yeah, so another question maybe before we wrap up, if anyone has it. Okay, well, hope this was useful, and appreciate the opportunity to talk with you folks. And feel free to reach out to me if something I might be able to help out.
Thanks for lending us your expertise today, Eric, and thanks everybody for being here with us.
Thank you.
Thank you.
Take care.
Take care.